A lot of you have been doing quiz retries, and all those grades are in. So keep it up. That's what you should be doing. So we're going to do a little bit of work with slope fields today and solution curves, and then we'll do our quiz in the second half of class. So a couple of fill-in-the-blank style things here. It says a slope field is a graphical representation of... Any guesses on what would go in those blanks?
Slope.
Well, it's blank, blank slopes.
Slopes.
So we could say slopes, but
That doesn't really make a lot of sense.
I don't get it. Yeah, I don't get it. Any ideas? We're going to take, it's calculus class. What kind of slopes have we worked with a lot? Say again? Okay, but then we kind of do something with those to get a simple approximation. Okay, and you said something about a slope? Joe? No. No?
I don't know.
Of course, let's play Wheel of Fortune. There it is. I wish I had a grand prize of a car, $20,000 to give you, but let's get all of our admiration.
She'll take an A on the test.
It would have no meaning, though.
An A?
No.
It would bring satisfaction.
You guys are so funny. It's almost like you have no idea what the purpose of a quiz is. It's like measure learning. I just gave her an A. It has no meaning.
It has a meaning of the grade.
That's kind of the point, though. I know you know this. All right. So, a solution curve is another thing we're going to look at today. Is the graphical representation of the actual graph, like the actual function we're trying to figure out here through a specified point. So we're going to start off by making a slope field, and I thought that I would do a couple of these for you, just kind of show you what's going on, but I'm guessing you guys will pick up on this super quick, and you'll be able to do a lot of these on your own, especially on this first one. So when you look at that, you can see it's called a differential equation. It's called a differential equation because it's an equation that has a derivative in it. If you look at that, you can see that dy dx depends only on x. And this is actually a little bit easier than the slope field you guys did on day one, if it was a circle at least. So I would say that my input is x, and my output is dy dx. So you know what we do here? We just start plotting some points, like we did on day one. So you could maybe go with 0. So 0 plus 1 is... So that means when x is 0, dy dx is 1. So what I would do here is I would attempt to draw in little slopes of 1 wherever x is 0. Okay? So wouldn't x0 be the y-axis?
Yeah.
So all along the y-axis, we'd have little slopes of 1. So I would put a little tick mark there. And I'm just trying to get it to be a slope of 1. These are turning out pretty nicely, I guess, huh? And I'm sure you guys can figure this out. What I'm trying to do here is I'm trying to connect that with that point. I'm just trying to connect those so that I can have my slopes of 1 be fairly precise. Does that make sense? When it comes time to do a quiz over this stuff or a test later on, I'll offer you guys rulers to be able to do something like that. Okay, so maybe then... we plug in a different x value. Maybe we plug in 1. What would be dy dx whenever x is 1?
2.
That's right. So now, of course, these are going to be steeper. Twice as steep, literally. We did this on day 1 of our class, I think.
I don't remember.
Like literally in August, I think. Pretty sure. Okay, so is this enough momentum for you guys to maybe wrap this one up? I'll just kind of work quietly up here, and we can compare notes as we go. I'm going to go to the left. I don't know what it is today, but this is one of the better slope fields I've ever drawn. Usually they are all over the place. I'm happy with that for sure. Let's see here. So 1, 2, 3. So, I don't know, once you start to get done, I'm seeing a lot of you guys have gotten near a finishing point here. Whew, that's a good one. Nice work. You guys are all doing good. Those are all absolute works of art. You should, like, get a frame. But you had some erasings, Hunter.
I do.
Still looks pretty good.
Laminate?
You should, yeah, like on the wall above, like the dining table or something. Maddie's. Love it. Okay. So guys, listen up. Look at my slope field. Look at yours. Do we agree? So there's an interesting pattern here to be noticed. Did you notice that in like every vertical column had the exact same slope field mark? Every vertical column matched, right? Now here's why. Our dy dx depended only on x. So whenever that's the case, you will get lovely vertical patterns. How do you think you could get awesome horizontal patterns within your slope field? Yeah, if it was dy dx equals and the only variable on the other side was a y, you'd get horizontal patterns. If it's dy dx depends on both x and y, that's where you start to get some diagonally patterns, kind of like that circle that you were mentioning we did on day 1. Okay, so now what we're going to do is we're going to draw a solution curve through the point -1, 1. So I want to define a little bit about what a solution curve is. So first of all, a solution curve must pass through the point given. We sometimes will call that point the initial condition. We'll use that language a lot coming up in the future. So in this case, it must pass through the point -1, 1. And hopefully that makes sense because it says sketch a solution curve through the point -1, 1. It's got to pass through the initial condition. B, it's got to match the slope marks. It's got to match the slope marks. So let me give you an example of a bad solution curve. So if I were to locate the point -1, 1, that would be this red point right there, right? So if I put a point right there, haven't I met the first requirement? Like my curve is going through the point -1, 1, right? But then if I were to draw my solution curve like this, do you see how that does not match the slope field marks at all? So that would violate condition or requirement number 2, right? So that wouldn't work at all. But if I were to then take this solution curve and do something like this, isn't that a lot more closely aligned with the slope field marks? And then maybe I would do the same thing over here. Nah, it's not quite as good. Can you see how that as I move through the slope field, that red curve really kind of matches? It's always going to be somewhat of an approximate art here because we're doing our best just by hand with pencil and paper, but it does seem to match the slope field marks. So requirement number 3 is not really going to be a big factor in this particular example, but it'll be a big factor in the other ones. The solution curve must be a function over the largest interval with the initial condition. Oh, sorry, I'm kind of getting into a bad spot there. are you serious? Okay, so let's whisper about it. Instead of just asking a direct question, let's whisper. You want to talk about it openly?
Sure.
Okay, so like I said, this last requirement is not going to be much of a factor on this particular example. Because isn't that red graph a function? Right? So, I think maybe on the next example, I think it is. The solution curve is going to end up being, like if you drew the full solution curve, it won't be a function. It would fail the vertical line test.
Okay.
Right? So we'd have to decide, are we going to choose the upper half or the lower half? Right? And we'll talk about how you can decide that. But I just wanted to give you the full explanation here. It's got to be a function. Is my red curve a function?
Yes.
Yep. And it's got to contain the initial condition. Does it contain the initial condition?
Yes.
Yeah. So that's why I say requirement number 3, it's not going to really matter for our red graph. But later on it will. It definitely will. Okay. So another solution curve it asks us to draw. So let's do that one too. It says sketch another solution curve through the point 1, -2. So 1, -2 is right there. That's not a very good color. Sorry, let me switch. So 1, -2 is in that green point. So let's see if you can get that solution curve sketched in there containing that initial condition. I'll do my best as well. What do y'all think? So if you had to take a guess at this, what would you say the solution curve is the graph of? You're just eyeballing this. It looks like a parabola, doesn't it? Can I prove to you that it really is? I'm getting way ahead of myself. Please don't feel like you need to scribble this down, what I'm about to do. Check it out. Ready? Starting to look like a parabola, like Merrick said, right? Well, then how would you find the C? Any guesses?
Initial point.
Use the initial condition. So if I did the red one, doesn't the red parabola go through -1, 1? I'm getting way ahead of myself here. So for those of you who are like, oh my gosh, you're going so fast, I'm never going to be able to remember this. This is going to be the next concept. Okay, so I'm just previewing the next concept. So if I wanted to get the red curve, watch this. It'd be 1 = 1/2 times -1 squared plus -1 plus c. So this would be 1 = 1/2 minus 1 plus c. So let's see here. That's -1/2. If I add that over, I get, what, 3/2 equals c? So my actual red curve would be y = 1/2 x squared plus x plus 3 over 2. Just like Merrick said, it's a parabola. Okay? So Zach, it's okay.
No, why does it make sense?
Why does it make sense?
Math, why does it work like this?
Isn't it lovely? Math is supposed to make sense. It is. Okay, let's do one more. And by the way, we'll do this again when I see you, when we have a regular class again, whenever that is. We'll practice this some more. So if you would, please take a look at our next page. Okay, this is gonna be a pretty simple day. We'll do the more complicated ones the next time we work on this. So please attempt to draw a slope field for this one. dy dx equals y minus 1. I'll give you a minute to get ahead, and I'll try to catch up to you. You guys are doing really good. It's probably going to be hard for me to catch up to you at this point.
Dang it.
You guys notice how you're getting a horizontal pattern within your slope field? Why would that be?
Depending on what?
Yeah, slope only depends on y. Can you also see how the steeper these get, the harder they are to draw?
Yeah.
They look vertical real quick. It gets hard to differentiate between how steep two slopes are right by each other. I'm having a hard time a little bit there towards the bottom of this particular graph. So yeah, so AP will have this every now and then. They'll have you sketch a slope field. I'll certainly do the same thing. It's not about me getting out a protractor and saying, Luke, the angle should have been 31.4 degrees and you had it at 32 degrees, so -1 or something. That's not it at all. If a slope is supposed to be negative, better be negative, right? If it needs to be positive, it better look positive. But then as far as like, slopes getting steeper or less steep, I'm just going to look at kind of the relative angle of each of them. Like if this slope is supposed to be if this is supposed to be less steep than this one, it better look less steep. Does that make sense? I'm just going to look at the pattern and say, hey, look, his slopes are getting steeper as he drops down below that y = 1 consistently. It makes sense. Same thing with the top, except they'd be getting steeper positively. So this is not an exercise in protractors and angles and that kind of thing. Hey, check out my slope field. Does it look okay to you?
Definitely wrong.
Mine is definitely wrong?
No, Reese's.
This is where you know what? It's hard with slope fields because it's all just like little line segments, and so if you go wrong, then it's just looking like a bunch of like asterisks that you try to erase and then replace, and it's tough. Can you also see why it would be foolish to use a pen when you're making a slope field? How well does it erase? Is this the trademark Hunter Blue?
Yes.
Okay. Well, if it erases well, that's fine. That works for me. You guys agree with this? Slope field? Any guesses on what's happening at y = 1? Oh, somebody said it. Horizontal asymptote. Yeah, you're about to see something cool with this. Let's draw a couple of solution curves here. The first one goes through 2, 1. So obviously 2, 1 is right here. So I've got to pass through that.
It should be a vertical or a horizontal line, would it?
It's going to be a horizontal line. It is, yeah. So, and here's why. Like I've got to pass through think about it like this. Here are the requirements. The solution curve's got to pass through the initial condition. Well, right now it does. It's got to mimic the slopes around that initial condition and throughout the rest of the slope field. And it's got to be a function over the largest interval containing that initial condition. Well, if I were to do this, let's think you might say, hey, I think it should go up like that. But think about what would happen. What would I need to do over here? Would I need to go down? Or would I do this? Or would I do this? Do you see how none of those options work? What I really have to do here is recognize that my initial condition is on a part of the slope field that's just horizontal regardless of the x. So my solution curve for number 5 there, I can actually do better than that. Would be a horizontal line right through there. Do you see how that is a function and it mimics the slope field around that initial condition and it goes through the initial condition? Okay. The other one is 1, -1. So that is right here. Do you see how this is not on that horizontal asymptote? So I'm thinking it should look, whoops. Something like this and like that. Do you see how that's a function, right? Passes the vertical line test. it passes through the initial condition. And can you see how it does roughly match up pretty well with those slope field marks?
Come back to understand the asymptote.
So like here,
Yeah.
is that a function? It's got to be a function.
It's tough.
So there's some really good stuff in there. Let me do this. I might be able to connect this for you, Luke. So check this out. What kind of graph does that look like to you all? Exponential is right on the money. So guys, this is one of those times. Hey, listen, please. It's going to be one of those times where I'm going to do some stuff pretty fast. I'm not expecting you to do what I'm about to do in the black pen up here, but hopefully everything will seem logical. First thing I'm going to do is I'm going to get my variables apart. So I'm going to divide both sides by y minus 1. You see I just basically flipped the y minus 1 on the dx. Mathematically valid. Integrate both sides. Oops. I already have an integral over there. You guys remember what the integral of dx is? It's just x. So I'd have x plus c. And do you know what the antiderivative of ln of y... That's why we don't do verbal quizzes. Isn't it natural log of y minus 1?
Yeah.
I gave it away myself. Well, where would the e come into play here? Check it out. Wouldn't it be e to both sides?
Why?
Because I'm trying to get the y by itself. If I'm trying to get the y by itself, I got to get rid of the natural log, and the e will undo the natural log. So it'd be absolute value of y minus 1 equals e to the x plus c. We actually did this very equation on the very first regular day of class right here. I've got to consider my initial condition here. I'll do the purple one. So let's see here. Y is negative 1 when x is 1. So I get absolute value of negative 2 equals, bless you, e to the 1 plus c. So 2 equals e to the 1 plus c. How do I get the c by itself? Yeah, so I go ln of 2 equals ln of this. So I get ln of 2 equals 1 plus c. So ln of 2 minus 1 equals c. I'm actually taking the long way here. You guys are probably like, yeah, you totally are taking the long way. So this would give me then absolute value y minus 1 equals la 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 plus, I know my c now is this. So I would actually end up getting, it would be this. And I know I'm skipping steps, but again, I'm not terribly concerned with you having this mastered right now at all. Not even close to mastered, the black stuff up there. I just want to prove to you that that indeed is an exponential. That makes sense? And so, Luke, if I tried to, because you said, hey, would this purple curve continue above the horizontal asymptote? So if I tried to do that, like if it did, wouldn't there be like a symmetry to it?
Yeah.
So wouldn't you think that if it did, wouldn't it go through this point right here? Right, because that'd be the mirror image. So that point is what? 1, 3? Yeah, 1, 3. So I should be able to make that point work if it's supposed to work. Oops. Be 1 minus e to the, oops. Yeah, 1, 3. So it'd be 3 equals 1 minus e to the 1 plus ln of 2 minus 1. Hope I have enough room to do this. It'd be 3 equals 1 minus e to the ln of 2, correct? So 3 equals 1 minus 2. Oh, wait, we have a major problem. It doesn't fit the initial condition. So that's why it's got to be a function. It's got to match the slope fields, but it's got to match it in a functional way. So you'd have to pick either the bottom or the top there. That's a little bit more than I wanted to do with that, but that's a great question. Thanks for asking. Okay, so again, I want to be crystal clear. If it's in black up there, right now, I don't really care if you know how to do it yet. Not in the slightest. I wasn't trying to teach you that. I just wanted to make a connection between your old graphical knowledge and this stuff. If it's a slope field, or it's red, or it's purple, I do want you to work on getting to a place where you have that mastered. We good? Okay, build a fort, please. I'll get you your quiz. Good job.